So I'm Chai. I'm head of AI research at Cruise. And first, I do thank the organizers for giving me the opportunity to speak here alongside so many experts in the robotics area. I'm super excited and a pleasure to be here. So I'll just spend one slide to talk about what we are. We are Cruise. We're a self-driving car company based in San Francisco. We have been trying to build the self-driving car for ride-hailing and delivery services. And actually, towards the end of last year, we achieved quite a milestone where we started operating driverlessly in San Francisco. We were the first to do that. That's really, cars without the safety, even a safety driver inside. Since then, we've also been taking members of the general public on our rides and has been successful so far. So now to our topics about kind of scaling, because the theme of this workshop is about scaling robot learning. I thought it's only appropriate for me to talk about our current effort in scaling the self-driving car in San Francisco and beyond. So when we talk about scaling the self-driving car, there are a few challenges that I'll outline here. The first thing that you think about is to scale to new geolocations. And by that, I mean, for example, new cities. Like here, I outlined Tokyo, where people obviously drive on the left-hand side for the starters, and people behave quite differently than in San Francisco. And you also have different weather conditions, like the snow here. And beyond different cities, we also have different landscapes where you have inner city versus suburbs versus rural areas. You might say that rural areas are easier than dense city, but there are challenges that are associated with rural areas only. Those are, for example, mapping becomes more expensive if you operate in rural areas. Now, the second area of scaling is about different hardware platforms. So here at Cruise, we have two different platforms, but as time goes on, sensors become cheaper and cheaper, and our hardware team is working tirelessly on the next generation of hardware as well. So designing a software stack that not only work on a particular sensor suite, but across different suites is becoming more and more important as well. And actually, even within San Francisco, there are still room for scale. And by that, I mean handling more complex situations and performing more sophisticated maneuvers. So ultimately, we want to, safety is the only thing that we don't compromise, but sometimes we have to compromise on, the speed of the journey and the smoothness of the journey. So that's why we think that even once we have a full operation in San Francisco, there will be years, there's more work to be done to improve our performance. So here, I'm just showing a video that's actually in simulation of such a complex maneuver that we could do going forward. So here you see two of our cars backing up into a parking lot at the same time. So this is not even a maneuver. It's not a maneuver that we're doing right now. This is not a maneuver that any human would do, parallel parking, back parking simultaneously, but it was be such a grandiose situation once you imagine you have hundreds of cars and back parking at the same time. Okay, so now I've talked about different challenges in scaling, and these are all topics I could be talking about today. So like domain adaptation, self-supervised learning, and so on. I think a lot of these topics have already been addressed even today and at the rest of the conference. So I'm not going to talk about these topics in particular. Instead, I think there's one topic that has not been sufficiently addressed, and that's uniquely critical for the self-driving car, and that is validation and testing. And this is particularly challenging when we think about scaling, because often we don't have enough data to even test our self-driving car. So testing for the self-driving car is very complicated. There are multiple stages, and the stage that I'm going to talk about today is in scenario tests. So you can think about this as, in the supervised learning concept, you usually have a a bag of test sets, and you want your software to run against those test sets to make sure that your new software can handle all these test scenarios well. So you can think, just to let me elaborate a little bit further. So you can think of this gray disk to be, all the scenarios you want to cover with your tests, right? So your goal here is to build an extensive test suite as much as possible. And so what should this bag of tests contain? So you'll find some nominal cases by just driving around, right? You're driving around the city, nominal cases, they contribute to maybe 99.9% of all the scenarios that you encounter on the road. So like driving straight, stopping in front of traffic light, stop signs, and slowing down for pedestrians. So these are easy to collect, but they are not so informative. So you'll also have a set of handcrafted cases. So those are cases where your self-driving car will struggle. For example, unprotected left turns, double parked vehicles, and so on and so forth. However, you need to fill the rest of the areas with test scenarios that you've seen in the past. Maybe your self-driving car didn't do well in the past, or there's some scenarios where your human driver thought it's challenging. It was challenging. So essentially, you have these orange or red cases. These are kind of past long tail cases. And why this concept? So this concept has worked well for San Francisco, where we have been operating for 7 years. But once you go to another city, right, you still have the nominal cases as the blue dots here. You still have your handcrafted cases, but suddenly the long tail, you don't have enough long tail cases to even demonstrate that your self-driving car is safe. So what can we do here? So the idea here is to find adversarial samples. So you take one scenario that worked well previously, and you try to find scenarios that will make it more and more challenging for your self-driving car. So I'll have two techniques and examples later, but overall that's the idea, and you can then sample scenario along the line that will increasingly challenge your self-driving car stack. And you can do that for any arbitrary number of existing scenarios in your test bag. You can start with something that from a nominal case, one of the blue dots, but you can also start with a scenario that was already part of the long tail. So to that end, I'll talk about two projects. One is called Adversarial RL Agent. The other one is called Robust Adversarial Scenario Generation. I know that they sound kind of similar, but the word adversarial is a little bit overloaded here. So you'll see. I can promise that they are completely different projects. Just for clarity, I'll refer the other road users as agents, and I'll refer the self-driving car, the autonomous driving vehicle as a self-driving car. Okay, so the first deep dive project I'm going to talk about is Adversarial RL Agent. So we have a lot of aggressive and unpredictable long tail cases and behaviors from other agents on the road. Just as an example here, we have an agent who dropped her hat and suddenly turned around. And here we have a bike who tried to avoid a car that's pulling out by going into the self-driving car's lane. And that forced us to hard brake. It's not something that I would have done as a cyclist. I probably would have stopped there. But this cyclist decided to nudge around the car, the other car that's trying to pull out. So these are exactly the scenarios where bad things can happen, and we need to be rigorously testing against these long tail scenario situations. So our answer here is to use reinforcement learning. I know that you've heard a lot about reinforcement learning today, but RL is such a natural concept to solve the self-driving car problem. However, it's so far I've yet to see strong evidence that we can use it for planning, because it's a chicken and egg problem. Right? As you know, if you have the perfect simulator, you can train your perfect agent, but then if you have the perfect simulator, you probably have this problem solved anyway. Now, but this problem, we can basically formulated our problem into an RL problem that's more sound. So essentially what we said is, can we train adversarial agent that tries to get hit by our self-driving car? And then we make sure that our self-driving car can handle well against those situations. But what we can do is we can have the perfect simulator because we have the environment, we know the physics, we have the self-driving car agent that's controlled by our own stack. And we have the agent policy from all the other road users who are trained to be adversarial. And now we can collect replays and train standard of policy RL agents and then iterate. So our reward essentially consists of do I get hit and how hard do I get hit? So these are really truly adversarial agents. And early on in the training, the agent will, so here you'll see the agent here and our car coming from south to north. But early on in the training, the agent will just say, okay, I'll try to nonchalantly cross the street, but they don't get hit because our car is smart enough to recognize that the pedestrian is coming out of occlusion and we should stop early. So no reward for the agent. Now, once the training finishes, it really learns really smart policies. So it learned that if it makes one step forward, the car will start to stop and it won't get hit. So in the end, the pedestrian got so smart, it just knows, okay, I need to last second, I'll try to move forward so I can get hit, right? So it just stands still for a very long time and it knows when it's time to make the first step. So now there are a lot of fun things that you can do with this adversarial agent. So here is a scenario where in reality nothing bad happened. So you have kind of a jaywalker here that came behind the occlusion, but fortunately the car, in reality, the car stopped and the pedestrian also, the jaywalker also stopped in the middle of the road and then proceeded once they realized that our car stopped. So in reality, it's all good. But can we make this situation more challenging for our self-driving car? Okay. So the next video is in simulations. You can see this is now sensor render. It's exactly the same scenario. It's still the pedestrian coming out of the occlusion, but now the pedestrian doesn't pay attention to our self-driving car at all. So the pedestrian just runs through the street. So it's arguably a more challenging case, and where bad things can happen. Right? It can only happen when both parties don't pay attention. So similarly, so I'll just play this video one more time. So you'll see that there will be two cars, and there will be the pedestrian coming out of the occlusion, right? And then the pedestrian not only didn't stop, it actually accelerated and really try to get hit. And in those situations, our car could still navigate safely around that jaywalking pedestrian. And yeah, here I will show a similar case. So now it's in the middle of the night. Actually, here you can see that why LiDAR is important, because you really cannot see that agent that well if you didn't have the LiDAR. But anyway, here is the pedestrian kind of ran jaywalk into the middle of the road, and then for some reason turned around. But again, in reality, nothing bad happened because our car stopped safely. The participating agent also stopped in the middle of the road, and then returned back to the original state once they realized that the car is coming. So again, here we can replace that agent with a kind of more aggressive agent. So here we assume, okay, that agent it cannot be predicted what they are going to do. So that you can see that this agent, after returning to the boundary of the road, came back to us, and we were still managed to brake safely in front of that pedestrian, and that's all what it matters. Okay, so that summarizes the adversarial agent, RL agent work. I think I have 5 more minutes, so I'll just talk a little bit about the second project as well. So it's about robust adversarial scenario generation. So here, the word adversarial is more closer to what you probably know from past work in adversarial generation. So the motivation is this. In the previous work, we knew what adversarial means for a road user. But for other elements in a scenario, you don't really know what adversarial would mean. So what is an adversarial traffic light, or what is an adversarial road? We don't know what that is. So essentially, here the question we are asking ourselves is, can we generate adversarial samples in a more principled way? So here we get inspired by the kind of seminal work by Christian Szekely from 2013, almost 10 years ago. And the idea is the following, for those who are not familiar with the work. So essentially, you have an image of a dog, and you have, back then you had AlexNet that does image classification that tells you, okay, this is a dog. Now, what you can do is to optimize to find the gradient from the image with respect to the loss, and that gives you a noisy image. And if you add this noisy image to the dog, you'll get something like this. To a human, it still looks like a dog, but the model will now say it's a cat. So this is basically what's known as an adversarial example. It's related to the to GAN and all those line of work. But the challenge is for self-driving cars, the validation is not so useful because this is clearly still a dog. The chance of this adversarial dog occurring in real life is basically impossible. So the question is, how can we generate adversarial examples that are robust across a different architecture, different models, and they are robust to translation, rotation, and so on. So the key here is to regularize the model. We need to regularize the model by quite a bit to make that happen. So essentially, we break down the model in the middle, and that gives us, so instead of one AlexNet, we now have an encoder that gives us an embedding, and we have a task that's essentially a classification system. And we do the same exercise of computing the gradient, but instead of propagating the gradient all the way to the input, we only do it up to the embedding, and that gives us a new embedding. Now we can have a decoder that generates the eventual image. And we apply the loss between the output image and the input image, and that basically is some kind of an autoencoder we're training here. There's one last problem which is there's no, right now if you just take the architecture like this, there's no guarantee that this image here, that the noisy image looks realistic because there's no loss for it. So basically, as a last step, we need to add a discriminator here too. So now, if you do that, you can then, even in the image space, you can, for example, generate a bird that actually looks like a bird to the human as well, and from this particular dog, right? So, and that's what we want. So essentially, we want to generate adversarial examples that has a relationship from the original input, so that the sample is still somewhat realistic, and it's adversarial. So we can do like fun things like finding all the interpolations between two samples that people have been doing with adversarial samples. And we can see, but the difference is that we don't actually have the ship embedding. So we have a car embedding, and we are saying, okay, how can we make this car more and more adversarial? And you can see that the car, with time, becomes something that looks like a ship, right? And the same thing with this car, and we make sure that it actually generalizes well. So we are not just generating one type of ship that would be a collapse in the model. So our model doesn't really collapse. So we ask. So here we have two cars. They end up being two ships that look differently. So now you can do this for self-driving. So here I have an example. This is kind of a toy example where you have 3 lanes. You have 3 cars driving in parallel. The orange car is a self-driving car. The other cars are the other agents. So you can do this similar exercise to make the situation harder for the orange car. And here what we see is really cut-in situations that were learned to cut in. So there's no hand tuning here that says, okay, I want the cars to cut in. And the scenario generation pipeline really found that cut in is the most dangerous thing that can happen here. And if you overdo it, then yeah, you can easily overdo it. In this case, both cars try to cut in at the same time and they crash into each other. And you can even overdo it more. And here you really, the other car, they cut in and then stopped right away. In this particular toy example, our self-driving car couldn't react fast enough to the cutting in vehicle. But this is just a toy example. It's not really our entire self-driving car. Okay, so I'll wrap up here. Today, I highlighted several challenges we face in scaling the self-driving car. I deep dive into the scenario test framework and introduced two projects. One is on adversarial RL agent, and the other one is on adversarial scenario generation. And if there is one message I'd like you to take home, is that you should feel 100% safe when interacting with our cars, because we've not only tested it against everything we've seen before, but also things that we think that are adversarial to our self-driving car. All right, that's it. Thank you.